So what about if you have a uniform spherical shell? Okay, what happens in that case? Well, there are some properties of the uniform spherical shell that we need to talk about. Number one, very important, this uniform shell does not exert any force if test charge is in its interior. Okay? And number two, at exterior points, this acts like a point charge, provided that it is further away outside. So let's do an example. So this is my thin spherical shell of charge. Okay. So if the radius of this is big R, and you were to place a test charge inside it, okay, it will experience no electrical field. And the reason is because there is no electrical field on the inside. Remember when we talk about electric field lines, they have to begin and end at some point, right? On the inside, they do begin, but they don't have anywhere to end. So there is no field on the inside. So for R inside, E is 0. And then for R greater than R, that means outside, E will be 1 over 4 pi epsilon naught Q over R squared. What about if instead of a shell, you now have a sphere? So instead of a shell, you now have a uniform spherical sphere. What happens in that case? Well, now this case becomes really interesting. If Q, let's suppose Q is the total charge of the sphere, then volume charge density will be equals to Q over 4 pi R cubed over 3. So now we're talking about a sphere, right? How do we deal with this? Well, instead of dealing with each point on this sphere, if I take a whole sphere, I can divide this sphere into many tiny shells, right? Into many tiny shells, each of radius little r, right? And then place a test charge inside the sphere, okay? What will we see? What we will see that this shell behaves as if all the things inside that charge were not there. Okay, so the total charge, it will be affected by total charge. So again, it's a uniform spherical, so everywhere there is a charge present. So imagine that this is a charge that's present everywhere. So in this case, what will happen? So the total charge inside the sphere, if this radius is considered r, and the total radius considered big R, right? And this is going to be big R, then this will be equals to Q equals rho V, which equals rho 4 by 3 pi R cubed. Now imagine this is not the big R, but it's actually the little r. And the reason why it's a little r is because this test charge only sees this as being interacting. Okay? Now, what do we know? We know that this Q is equals to this rho is 4 over 3 pi r cubed times 4 over 3 pi little r cubed. 4 over 3 pi r's go away, and we get Q r cubed over big R cubed. Okay? So now in this case, your E will become 1 over 4 pi epsilon naught Q over R squared. But my Q now is equals to this. So I can plug that value in here. That will be 1 over 4 pi epsilon naught Q R cubed over big R cubed divided by R squared, right? And I can solve it a little bit to give me E equals 1 over 4 pi epsilon naught Q R over big R cubed. So for a test charge on the inside, the electric field is going to be given by this amount, not the total. So it's going to only see this little thing that the radius is going to act on it. Everything else, it won't even see it. So summarizing, if you have a volume and it is a cylindrical volume, your total volume is going to be pi r squared L. dq will be given by rho dv. Rho will be given by q over v. If you have an area, it's going to be width times length. dq will be sigma dA. Sigma is q over a. And if you have a length or a one-dimensional surface, then it will be dq equals lambda dl. And lambda will be q over l.